first of all, what I need to do when I look at these three functions I have here that I'm given, I'm going to be using these three functions to create new functions. And one of the things you're going to be asked to do down at the bottom there is basically if the result is a rule, then state its domain. So that means that if the answer I'm going to be getting is going to be some sort of algebraic or mathematical expression involving a variable, then I should also be prepared to state what the domain of that particular function is. And I have to be careful about that because I mean I just don't look at the function that I end up with, because if I look at the function I end up with, there could have been some things that went on between various functions to create that final result that may have done some cancellation of things. I have to keep in mind that, if it's the result of me not just composing, but basically combining two different functions together in some way, and some things may cancel each other out as a result, um, you know, then I have to keep in mind that well, that all that stuff happened because I was able to carry through that operation with those two functions. And that being said, that means the two functions had to have originally existed. So I do have to consider any function's original domain as I get started in making up a brand new function involving it. So I got to look at the three original functions here as domains. When I look at f of x, for instance, I'm taking x and squaring it. I'm subtracting a 3 times that x. I'm subtracting 10. There's really nothing here that says, well, there's x values I can't square. Well, I can square any value of x I want, as long as it's a real number. I mean, any real number can be squared. Any real number can be multiplied by 3 and then subtracted from the square of itself. And and I can subtract 10 from all that mess. I mean, so there isn't really any x value that says, hey, I can't do it with this. When I look at g of x, though, I see that radical, which is another name for that square root symbol. That radical basically tells me that, well, there's certain numbers that when they're underneath the radical, I can't do. If there's any x value that would make the expression 9 minus x squared negative, well, that can't be included. So if x would happen to be more than 3 or less than negative 3, I would get a negative value under there. So I'd have to exclude those and basically say, well, numbers between negative 3 and 3 would be the domain. And for j of x, that fraction bar and a variable in the denominator is another key thing I would look for. So, since the bottom of this fraction can vary, I don't want any instance where the bottom of this fraction could become 0. So I had to say, well, what would make the denominator, the bottom of this fraction, 0? Well, if x were to equal 6, this would become something over 0, and that's undefined. So I would have to say, well, it's all real numbers there except 6. And that's what these three domains come from. Now comes the next part. It's like, okay, well, it says, if the result is a rule, state the domain. So basically it's saying, well, not all of these are going to be a rule. Not all of these are going to be some sort of algebraic expression. When I look at these three here, these three questions, all of them are going to have a very similar look to them. You're going to have two quantities. Some textbooks may or may not put the parentheses around the function letters. I mean, so I have to know which letters represent function letters. F is the result of me doing several different things to an x value oftentimes. And same thing with G. Those are function letters. And then the second quantity is either going to be a number or a variable, typically x. If I see a number in that second group of parentheses, that indicates that the answer I'm going to get is going to be a number. Okay? So I should know immediately, like I know, for instance, in A, I'm going to get a number as an answer. When I look at B and C, the fact that I have a variable in that second parenthesis, I know immediately I'm going to get some sort of algebraic expression as an answer, and I need to be prepared by stating the domain once I'm done with that. So there's actually two parts of the answer, the rule itself and the domain. When I look at A, f plus g of 0, what it's basically saying is, okay, well, if I take the function f of x and g of x, add that together, I would get a brand new function, which would have its own domain and everything. Well, what happens if I take that brand new function and plug 0 into it. And that's the way the textbook actually asks you to do it. Not needed in this case because I'm only asked to find what happens at 0. So essentially what I'm going to do for this to make, kind of like, make my life a little easier, f plus g of 0 is the same thing as doing f of 0 plus g of 0. It kind of looks like the distributive property, but I'm not really multiplying the 0. So I don't want you to think of it as being distributive. If I go to the function f, put 0 in the place of x, I get negative 10. If I do the same thing with the g of x and replace all its x's with zeros, I get the square root of 9, which becomes 3. And of course, negative 10 plus 3 is negative 7. So that's my answer. When I look at g minus j of x, very similar, that's the same thing as me doing g of x minus j of x. The only thing I can substitute here is, is what g of x and j of x are. It's going to basically going to substitute the right-hand sides. And so that would be the rule for the function. Sometimes you can simplify them, you need to kind of be on the lookout to see if it can possibly simplify. For me to have a function made up of the subtraction of two other functions, those two functions have to exist, both of them at the same time. So what I'm actually looking for is a domain that satisfies the two original domains of g of x and j of x. So here, the domain must satisfy being between negative 3 and 3 and all real numbers except 6. If I'm only taking values between negative 3 and 3, that means that 6 is automatically excluded. So I don't really have to do anything different. If I satisfy g's domain, I already satisfy j's. And that's why the domain is negative 3 to 3. F times j of x. Again, that's the same thing as f of x times j of x. And I can write that as such. And any one of these expressions would be possible answers, because they may say, well, x squared minus 3x minus 10 could factor, and they do expect you to know that. Although we haven't gotten into discussing factoring a whole lot yet, because we haven't talked about quadratics exclusively. But again, they do, this textbook and the university does assume that you've had the algebra necessary to be in a pre-calculus course, and so you have done factoring before. So I could even have it in factored form in the second line. I could have, once I do the multiplication, I could put all those in the numerator, leave the x minus 6 in the denominator. Whatever the case may be, any one of these would be an acceptable expression of the rule. But again, I had to look at this and say, okay, for this function to exist, the multiplication had to have been carried through. And for that to happen, both the original functions have to exist. So I'm looking for a domain that satisfies all real numbers and all real numbers except 6. Which means in this kind of situation here, it's going to take the one that's more exclusive, which means all real numbers except 6 is going to be my domain. Some more examples. F of g of 3. F g of 3. Again, if I have two, those are two function letters next to each other. Anytime I have two anythings next to each other, variables, a number and a variable, with the exception of two numbers right next to each other, like 3 and 3 next to each other is 33. But this is f times g. So the same thing as doing f of 3 times g of 3. So I'm going to go to the function f, put 3 in its place, and I get negative 10. I go to the function g, put 3 in its place, I get 0. And so negative 10 times 0 is 0. When I get a situation where division becomes involved, because the first thing I'm going to keep in mind is that g of x over j of x is g of x over j of x, and that's how I would write the expression. Okay. And as you see, I am putting something that has x's in it in a denominator. So that alone is going to often cause additional possible restrictions, additional constraints, if you will. For instance here, if I carry through all my rules of fractions and carry through the multiplication, and so since I'm dividing by 5x plus 1 over x minus 6, that's the same thing as multiplying by x minus 6 over 5x plus 1. That's how the x minus 6 ends up in the numerator. The reason why I make sure to show this is a lot of students at this point would say, well, that means that x could be 6 again. No, it can't. Because, yeah, it's in the numerator now, but it only became in the numerator because I carried through a division, which means that j of x had to have existed, and for j of x to exist, x cannot be 6. Pure and simple. So it's not going to bring in any additional things. I mean, once I get a restriction going, I say, okay, here's what it's restricted to. If anything, if I do other operations, it's going to restrict it further. It's not going to take away restrictions. So, as far as the domain goes, it has to satisfy the domains g of x and j of x, and any new constraints I would see. Because as I see here, I have to first satisfy x is between -3 and 3 for g of x. I got to satisfy all real numbers except 6 for j of x. And if I look at what I have now, that 5x plus 1 now being in the denominator, means I have another potential x value that could put a 0 in the denominator. And that x value, by the way, would be -1/5. So if x is -1/5, well, that's going to cause an issue and give me a 0 in the denominator. So that's what I mean by a new constraint. So these are the three domains I more or less have to combine together to form one domain that satisfies all three cases. Much like we mentioned before in the previous problem, I'm not going to get rid of it because of the fact that it's the x minus 6 is no longer in the denominator. I'm getting rid of it because if I say that x is between -3 and 3, if I'm satisfying the first one, this one's automatically satisfied, so it doesn't need to be said because the first one already excludes 6. The third one now, the problem I have with that one is that, well, -3 to 3 does contain the value of -1/5. So I got to take that -3 to 3 and now say, okay, it's going to be that, but now I got to throw out the -1/5. So the way I would represent that is to say this. I would go from -3 including it to -1/5 excluding it, and then do a union of that of the interval of starting at -1/5 not including it and going up to 3 including the 3. J over f of 3, again that's j of 3 over f of 3. I'm just going to evaluate the two. J of 3, if I put that in, I get 16 over -3. F of 3 is -10. If I carry through the division, if I divide a fraction by an integer, it's the same thing as me multiplying the denominator by that integer. Again, that's a rule of dividing fractions, and it's a rule that you're expected to already know. So 16 over -3 divided by -10 would be 16 over 30, which would reduce to 8/15, and that's what the answer for this one would be. J over f of -2. Now, when I look at this thing here, I look at j of x. Well, j of x, excludes 6. -2 is not 6. Looks like we're good. F of x includes everything. So, we wouldn't think, hey, there's no problem here. But, if we actually explored and figure out what the domain of j over f of x would be, we would see there would be a problem at -2. And here's why. Here's what happens. Of course, this is going to be j of -2 over f of -2. There is an error with this. I mean, because I think, it's one of those times I got interrupted by my kids as I was doing this thing. This should actually be, I'm doing j of -2, not g of -2. That's what would happen if I got g of -2. This should actually be reading, that should be in negative, bear with me for a second here, -9 over -8. So this should be a 9 over 8, not the square root of 5. Doesn't matter so much. I would get the same answer because the f of -2, if I put -2 in for the x's I see in f of x, I would end up with 0. So 9/8 divided by 0, dividing by 0 is going to create an undefined, no real solution, no answer type scenario. So that's why it's undefined there. For h, we have a new symbol here. This is the fifth operation. This is composition. And if I compose two functions together, what it does is it takes, I plug a number into one function, I get a result, that result becomes a domain value for the second function. So for instance here, if I'm doing f of g of 0, it's the same thing as me doing this, f of g of 0. And it still works with the order of operations. I mean, I have multiple parentheses here, and when I have multiple parentheses, I always work my way from the innermost one to the outside. So if I'm evaluating this following my order of operations, I'm going to do g of 0 first. So I'm going to go to the function g of x, replace the x with 0, and I'd get the square root of 9, which is 3. So this would become f of 3. And I would go to the function f of x, replace the x's with 3's, and I would end up with negative 10. So the answer for this is negative 10. Composition, much like subtraction and division, is also not commutative. If I do g of f of 0, that's what this is. And so I start with f of 0 first. That's going to be negative 10. So I'm going to do g of negative 10. And when I do that, I get the square root of negative 91, which again, we're only considering real numbers when we talk about domains and ranges. So there's no real solution around it's undefined here. Compositions do cause alterations, and that's why when I handle situations like this, where I'm going to obviously need to come up with a rule and therefore state the domain of the function, I have to have a special procedure for that. Of course, this means j of g of x, and I worked the whole thing through here. I replace g of x with the square root of 9 minus x squared. And then I go to j of x and replace each x with the square root of 9 minus x squared. So if you look right here and here, those are where the x's were. So you still see I'm still doing that complete removal and replacement. I'm not just like putting a 9 and a minus and a square root symbol in some arbitrary place. I'm taking the original x out and putting this whole expression in its place. But anyway, that would be my rule. What's its domain? Okay, well, first and foremost, I have to make sure it satisfies the domain of g of x, because g of x has to happen and be plugged in and to occur for me to have something to plug into j. Okay, so the innermost function's domain has to be upheld, and then I just look for any new constraints, because j of x is being altered because I'm no longer using x anymore as my variable. I'm using a result from g of x as my input value. So that's going to alter the function in a way that it's also going to alter its possible domain. So what I need to do is look for any possible new constraints. When I look at this one here, okay, what any new constraint would be, obviously I still have the radicals of the 9 minus x squared. So between negative 3 and 3 still is going to need to be done for those. I mean, that's what the domain of g of x was, so no difference there. Now I also have to look and see, was there anything that would create a 0 in the denominator? And I could go through really quickly here. I'll go through on this up here. Well, if I do like the square root of 9 minus x squared, the only way for that to happen is if this equals 6. Now I'm not going to show the entire solution process. If I square both sides, I get 36, which means I have 9 minus x squared equaling 36. Well, for me to start off with a number 9, subtract something from it, and end up with a bigger number means that something I'm subtracting has to be negative. X squared is not going to be negative if I'm only accounting for real numbers. So there's no way that the bottom is going to become 0 in this scenario. So there are no new constraints. So basically, if I satisfy negative 3 to 3, I'm good. I'm not going to have anything that's going to make the denominator 0. Therefore, negative 3 to 3 is my domain. If I want to do h of g of x, again, that's what this is. I'm going to replace g of x with the square root of 9 minus x squared, which means I'm going to go to the function h, replace the x with the square root of 9 minus x squared. And if I go through and simplify, I would get 2 times 9 minus x squared, because the square on the outside here and this radical, they would cancel each other out. And so I end up with the expression 18 minus 2x squared. Now, if I came up and said, okay, what's the domain of the function 18 minus 2x squared, you would say, well, there is no restriction. It's all real numbers. And I would agree with you. But this was obtained through the composition of two other functions. If that's the case, for me to have even gotten this far, the innermost function has to have existed. So here, this wouldn't even come this far if g of x didn't occur, and g of x would not occur unless x is between negative 3 and 3. So I still have to state that as the domain. mean, yes, the final one there's no constraints, but I still have to state here that it's negative 3 to 3 because that's what I needed to get g of x even involved, and g of x, had to exist.